since, oh, my apologies. Lukasz has been in Google since 2013. He got a master's in University of Wroclaw in Poland, and a PhD in France. I don't have the university in front of me. So could you confirm where you got your PhD?
At RWTH Aachen.
That's great, yes.
In Germany.
And he's obviously, Lukasz is a big name in NLP and AI. He was one of the founders of TensorFlow, as well as one of the founders of transformers, which have revolutionized NLP in recent years. So with that in mind, I want to, there we go. Okay. So with that in mind, let me introduce, let Lukasz begin his presentation.
Hi. So yes, I've been working at least in the last few years on sequence models, so deep learning for models that model sequences of things, and these things, especially in NLP, oftentimes are sequences of words in the language, even though, as you'll see, they could be sequences of other things, and it was. Like 10 years ago, you would think about this as a very academical endeavor. Like some of the best language models were still n-gram models, and n-gram means just you look at the previous two words, you calculate statistics from your corpus, and you have a probability of the next word. And these are very fine models, but they never excited people to the extent that we have now, because they could not look much into history. So you couldn't say, like, you couldn't think that they'll do things like translating languages or chatting with you or all of the things that NLP models started doing these years. So then came the deep neural networks. We model language and sequences with deep neural networks, and a big challenge in modeling sequences is still, how do you look at the context backwards? How long can your context be? So I will tell you about our recent work on that, which is called Reformer. It's an improvement on the transformer model to allow really long context and to allow it to run efficiently. But I also want to give you a broader context of how deep learning came to NLP, how the transformer models came to be, and some perspectives on what will happen. So I will try to keep this thing fairly general, with links to places where you can read more, but also, well, it's a virtual setting, so it's oftentimes hard to like speak directly, but if you have questions, maybe you can write on chat or just turn on and speak. I don't know if there is a way. In any case, don't hesitate to interrupt. I would hope that we can have like a that it's not just something to record, but also something where if you have questions, I can also answer them, even though I believe there might be an opportunity after the talk as well. So with that said, yes, so as I said, I work on modeling sequences, and the main application of this is NLP, natural language processing. But what is NLP, and what does it mean to apply deep learning in NLP? So NLP has traditionally been worked around a number of established problems, and these problems are like part of speech tagging. So you get a sentence and you need to tell for every word what part of speech is it. Is it a noun? Is it a verb? Parsing is another example. You get a sentence and you want to build a tree that's a grammatical decomposition of the sentence. Named entity recognition. As you get a sentence, you need to recognize entities in it. New York or Barack Obama, these would be examples of entities. Language modeling is another example where you try to give probabilities to sentences in language. And this was earlier kind of more of a niche problem in NLP. And as you'll see with deep learning, it has changed to kind of be the problem in NLP, which we'll get back to. But the earlier, the problems that people were like looking at, and then these are more like applications, is translation, right? Given an English sentence, give me the French one, or given a paragraph, translate it. Compression is important in cases like assistance for Google. So you have a paragraph and you want to just say one sentence that has the most important information. Like if an assistant needs to read out from a paragraph on a web page to you. So this is very related to summarization. And it can be abstractive, meaning you just pick words. That's how people used to do this earlier. These days, the models can do extractive summarization, meaning they can use other words than the words that appear in the paragraph. And question answering, sentiment analysis, these are the problems that we talked about in NLP. And should we move the slide? Hello? Oh, yeah. Thank you. Sorry for the inconvenience with that. These were the tasks about say 6 years ago. People in NLP were working on them, and the question back then was, can deep learning even approach these tasks? Because the way they were usually being solved was, you build a system, a part of speech tagger. It has some probabilistic components usually, but it also had some linguistic components. And a parser would build a tree with some grammar. So when deep learning came to the field, it was kind of like, there's this crazy idea that we solve all of these problems with these sequence-to-sequence networks. We put a sequence on input, and that would be usually the sentence that we're analyzing. And on output, we get another sequence, which usually would be the result that we want to produce. And the result could be either a translation of the sentence or like the sequence of part of speech tags. This would be the way that you do deep learning. And the idea that you could just do that, meaning have one network that takes an input and produces the output, and you train it on some data and it gives good results, this was kind of crazy even 6 years ago. Like, people were like, well, but wait, there is a lot of work, like a lot of linguistic knowledge that you need to have to build this, and that can't be that like just a network, especially a fairly simple mathematical network, like the early ones were long short-term memory networks, LSTMs, would just recurrently go over the input, produce the output, and that would work. That was considered like, well, maybe, but it should not work very well, right? And the next slide, well, it shows you that, well, it actually does work very well. And the first slide, like the first problem that I'm showing that it works very well, is this language modeling, right? Language modeling is given a previous words predict. Oh yeah, hello. Is it all okay? Given the previous words predict the next.
Hello.
Word.
Oh, Colin, hey.
Can someone please mute her? I do apologize.
Hello. So yeah, I guess if you have questions, it may be better to write them on chat, and then we can make a break and answer them and go on. I guess that may work better. So language model. What is it? Well, it's theoretically it's giving probabilities to every sentence. In practice, it's you have all the previous words in a sentence. You give a probability distribution of the next word, right? And so in layman's terms, it's autocomplete, right? You have written some text, and then you get the suggestions of what's the next word. And now this seems like a kind of, not as interesting as translation. And the baseline, which is here, are n grams, meaning 5 grams or 9 grams. Grams meaning like 5 grams means you look at 4 previous words and have the statistic from your corpus on the next word, and then you maybe smooth it in some ways. That's the probability of your next word. And it's useful, right, for your phone keyboard. And the performance of this is measured in perplexity, meaning on a holdout set, what are the probabilities you're assigning. And the lower the better. And there is a data set called LM1B. It has about 1 billion words. That's why the 1B. And people were like, okay, 67 is great. And then RNNs came and improved on the n-grams to 51. That was really nice. And people thought, okay, so the RNNs actually work here, but they work a little bit better than the n-grams, and that didn't seem so smart at all. And people kind of thought that, 40 is the perplexity that a human would achieve, meaning knowing all of the context and really knowing the language, you'd be able to get to about 40. And then suddenly the thing that happened was the RNNs just got bigger. So you see between the middle one that's an LSTM and the next one that's a 2-layer LSTM, it's just bigger. There's not much else, but the perplexity goes from 54 to 30. And then you make it even bigger and it goes to 28. And this is a pattern that you'll see with this deep learning work, that while the previous techniques that were very specific, human implemented techniques reached a plateau, they stopped improving. The deep learning techniques, they just get better and better the bigger the network is. And there is a downside to this, right? The downside being that we need to train huge networks, and this is sometimes expensive and takes forever, but they do get better and better. And so on the next slide, you can see the same pattern in translation. Like phrase-based models that were before the deep learning revolution were about like 21 BLEU score. BLEU score is the higher the better, right? Then early RNN models were a little bit below them. Then larger ones started matching them. Then they grew even larger and got even better. And nowadays they reach translation that's sometimes, at least for news language, on par with human translators. So how does this actually work? So on the next slide, you will see this is a picture for an RNN, which should be an animation, but isn't, but whatever. An RNN is a recurrent neural network, so it consists of an encoder. It processes input by input, state by state. So it processes E0, updates the state, then E1 updates the state, and so on until the end of the encoder sentence. And then it generates the decoded sentence using the state from the encoder, and then it generates the first decoded sentence, puts it into the decoder, back generates the second, and so on and so on. And this was the model for the first few years. And it, as you've seen, if you made them big, they work really well. They were better than the previous methods. And it's really a fairly simple architecture compared to all the work you needed to do in NLP before. And you apply it to problems and it works okay, quite well. But it has a few problems. One problem is speed. So the RNN to get machine translation to work better than a phrase-based system took about a month to train on like a few hundreds of GPUs back then, and about 5 years ago. So this was like, we could do this at Google, and this actually was the first launch of Google Translate that used neural networks. But it took a tremendous amount of effort and engineering to get these networks to train and get them to really good quality. It also took a lot of data, and it worked for translation because it works sentence to sentence, right? Your input is one sentence, your output is one sentence. They're not too long. When the sequences became longer, when you went to like paragraphs, gradients started to vanish in these RNNs. So they were super slow to train, but they also had a fundamental problem that sequences were vanishing when the length increased. So then we were thinking about this problem and found a solution that was based on an attention mechanism. Attention is a mechanism to, I think we can go to the next slide and actually one but next directly. The one after that is the transformer model, which is a model that instead of RNN layers has pure attention. So what is attention? Maybe let's jump to the next slide directly. We'll get back to the full architecture. In an RNN, you process the next word given the state from all previous ones, right? In attention, you look at all of the previous words at the same time. And there are actually three ways of doing this. So one way, that one was introduced before the transformer model, is when a word of the decoder looks at all of the words, meaning activations in this case, of the encoder. So this is useful if you're generating a French sentence. You look into the English source and attend, meaning get information from all of these words, and you hopefully pick the corresponding ones. Now, the ways introduced in the transformer are the encoder self-attention and decoder self-attention, which is when the words in the encoder sentence or in the decoder sentence look at their neighbors. So in the encoder, they can look left and right because we're not generating, and in the decoder, it needs to be masked to look to the left. So we are not using future to generate the words. So what is attention mathematically? Let's go to the next slide. If you know a convolution layer, right? A convolution layer looks in the neighborhood of an element, and it has a separate weight for like the element 1 to the left, the element 2 to the left, the element underneath you. So there is a fixed window, say, of 5 elements, and every one of those has a separate weight or a small weight matrix, and it's aggregated and creates the activation for you. So when you think of active attention, you should think that it's in a way similar, but convolution has this like item-based lookup. It has a weight for element I, a weight for element I minus 1, and so on, while attention is a content-based lookup. So it will not have weights per position, I minus 1, I plus 1, I plus 2, and so on, but it will have weights per content. So it will get some similarity score. How similar is this element to what I am asking about? And multiply all of them by this weight. That's the idea behind attention. And on the next slide, you can see how it is actually implemented. What's the equation for it? And it's deceptively simple. So if you have a set of queries Q and a set of keys K, then the similarity that we're talking about is computed as softmax of Q times K transposed. And you get this similarity matrix and multiply it by the values. So the equation for attention is softmax QK transposed V. Now you can ask yourself, why is the similarity computed just by a softmax of matrix multiplication? So think about it like that. If queries and keys were vectors of length 1, then QK transposed would be a matrix of size length by length, right? That in every element has the cosine similarity of these two vectors, because the dot product of vectors is their cosine similarity if they have length 1. Softmax, on the other hand, will allow you to focus on the most similar ones among the whole row. So that's it, right? We basically measure cosine similarity, softmax it, and use this as similarity to multiply vectors. Now, the thing I told you, assume they have length 1, they don't, and it's actually a feature, not a bug. the feature is because long vectors in the softmax they can change the temperature of the softmax. So they can force this attention mechanism to attend either a bit flatly to like all similar words in the sentence to act as a kind of a pooling mechanism, or they can have long wait and then the softmax acts very pointedly. It just selects one, the most similar element, and that's it. So that's one comment about that. And the other comment is about speed. So if you look at these equations, Q, K transpose V, you have two matrix multiplications and a softmax, which is a pointwise operation, right? I mean, it's a summation over rows and a pointwise operation. So these are very fast operations on modern accelerators. Since we have hardware that's built especially to do matrix multiplications very fast, this runs really well as long as the matrices don't get too large. So on the next slide, you can see, like if you think what is the O level complexity of the computation you need for attention? Well, if you have D as the depth of your vectors, so every vector is of dimension D, and your sequences of length n, queries, keys, and values, all of the same n, then the attention would take n squared D. And there were other forms of attention in use before, and they would have the same complexity. While RNNs and convnets, they would be linear in n. So you'd think, oh, that's better, right? We like linear things. But they'll have the D squared because they have a dense matrix in them. And if you look, so linear should be better than quadratic, right? You're like, oh, that's nice. But actually, like the sequence length, how long are sentences? There may be 70 words when they're really long, or usually they're like 40 or 20. 100 words is a long sentence, it borders on a paragraph. While D in the big networks, it's 512, 1,000. So in practice, oftentimes D is larger than that. So moving the square to the attention actually speeds it up in some cases, but not in all, and we'll get to that too. So, okay, that's the attention mechanism. And would that be it? Not yet. And I think we can go to the next slide and the one but next maybe directly. So when you were thinking about this convolution and attention thing, what you notice that attention has one weight for every element, while convolution has more weights, right? So it has more capacity, while attention is just a weighted average. So how would we distinguish where the places came from, and how would we add more capacity? And the fix to this is positional embeddings and multi-head attention. So on the next slide, you can see, yes, so in the multi-head attention is basically we perform in parallel a number of attentions, but the queries, keys, and values are generated with a different linear transformation. So in the slide one after that, maybe this is a better picture to understand. The scale dot product attention is attention as we just said, and they will be H of them. H is the number of heads. And when you have activations of a sentence coming, right, they will be the same activations will be used as the source for both queries, keys, and values, all three of them. It will come from the same thing, but it will be subjected to a different linear transformation, meaning just a dense layer, right? So queries will be generated for every head with a different dense layer from the activations. Keys will have their own dense layer, again, different for every head, and so will values. So we'll generate just a number of parallel things, compute the attention, get the results, concatenate them, and subject them to a final linear layer. So this is how the multi-head attention works, and it really helps to have a few heads running in parallel. Okay, so the multi-head attention, if we go to the next slide, it adds back the d-square term in complexity. So this is just something to keep in mind, and you can though make sure that it uses only as much memory as the head dimension, which is usually d divided by h. But I don't think we need to go into that. Let's go to the next slide, which is, here is the transformer. So what is the transformer? You use bidirectional attention layers in the encoder and masked attention layers in the decoder. So you get your input sentence, you add positional encodings, and positional encodings in the simplest but working very well case are just learned vectors for every number from 1 to whatever would be the maximum length of sentences you expect to ever process. So say from 1 to 1,000, you have a learned vector for 1, a learned vector for 2, and so on. And you add them so that the attention can know which positions to attempt. You add them to your embedded input sentence, then you have a number of multi-head attention layers, as you've seen, inside residual connections that also have layer normalization, which isn't necessary, but it helps training with higher learning rate. And then there is a feed-forward block, which are big ReLU dense layers. So it's a dense layer with a ReLU to some bigger size usually, and then another dense layer to a smaller size. You add a few dropouts in there to regularize things. And you build the decoder in the same way, except in the decoder, you'll have two kinds of attentions, right? One will be the masked self multi-head attention. So this is the same as the encoder, except it only looks to the left because when you'll be generating, you don't know the future. And then you have the encoder-decoder attention, which gets the queries from the decoder and the keys and values from the encoder. That's where the arrows are supposed to indicate. And on top of that, you put the feed forward. So that's it. That's the transformer model. And as I said, the attention is a very parallel, fast operation of modern hardware. It's basically a matrix multiplication. And the fact that we moved to n squared from d squared also helps with speed on sentences. So if you look at the next slide, these are the blue scores for machine translation. And as I told you earlier, it started with like 2021 for the pre-deep learning systems. And it was a big achievement and took like months of training to get to 24 with RNNs, and they were really big. So the training cost, see, it's like 10 to the 20, whatever. It was 10 to the 19. It took really long to train. It was really tough to make it all work. Then with the transformer, this was quite shocking because even the base model that took like maybe 2 days to train on like 8 GPUs back then, and now you could basically train it in probably a few hours. It already went to a blue score of like 27. And then you increase this model a bit, and it was still much faster than the RNN model. And the blue score jumped to 28, and now it goes to 29. And basically, I think people have gotten to almost 30, but it kind of loses any meaning because 30 is the score where you're evaluating it against human translators that also get about 30. So you need to start asking whether your references are not actually worse than the translations the model is generating. So that was a huge success that seemed to work much faster and give really nice results. And later, when we kept thinking about it, we believe that the really nice results are also the result of the fact that the attention does not suffer from this diminishing gradients with sequence length, because it can, in one hop, look at any other word in the context. So that was the transformer. And then on the next slide, you can see, so, well, this was translation and you could generate the next word, but how about other NLP tasks? And with other NLP tasks, there is a set GLUE, which is a set of NLP tasks, and people tend to measure an average score on these tasks. And if you try to just apply like bag of words methods to these tasks, you'd get an average score of about 58. If you apply RNNs with attention, you get about 65. And then what people discovered was that if you pre-trained, so Elmo is a way of pre-training on a large language model, or just language modeling just predicts the next word. So you can pre-train on a huge text corpus, whatever you pick, right? Just using some form of websites, and the corpus from the web is a popular pick. Then you get to 70, and that's nice, but like humans get to 87-ish, right? So there was still a big gap there with the RNNs. And then people came up with BERT, which is just the encoder part of the transformer, but pre-trained in a very smart way, so that you remove a subset of words from the sentence and you train it to predict these words. That the key idea is you just make gaps in the sentence, and it's a good number, seems to be 15%. So you remove 15% of the words and train just the encoder to predict these words. So the input is as it was, but with some mask in 15% of the places. And the output, you only score on these masked places it's supposed to predict. And you use this as pre-training on a large text corpus, and then on top of that, put your classifier, and it jumps to 80, and then you add things like recurrence in the models, which is Albert, and you can indeed exceed human baselines on the glue tasks. So that's a really big success, because you have one recipe that seems to solve basically all NLP tasks. So something that was kind of considered impossible 6-7 years ago, or maybe even 5, now is commonplace, in the sense you can just take off the shelf transformers and they will generally solve your old style NLP task. So great. Are we all done? Well, not fully, right? So one thing to mention is, how about non-NLP tasks? And actually, we can go to the next slide. The same idea of a transformer works in, as I said, I'm interested in sequence models. They don't have to be sequences of words. They can be sequences of pixels, right? So you can generate an image from left to right, pixel by pixel. It's not clear whether that's the best way, but it's an easy way. And you can give it as input, say, a low resolution of the version of the image, or some part of the image, or nothing. And it works fine, right? It generates images, it can generate music, it can generate other things. So transformer models work in general in generation. So that's okay. But what is more interesting, and what comes up when generating things like high resolution images, which have a lot of pixels, is how about length? So if we go to the next slide, it's like, what if you want to generate long text? And this is an example of an OpenAI GPT-2 transformer. So GPT is a generative pre-trained transformer, which is, in contrast to BERT, which was just the encoder block of the transformer, this is just the decoder block of the transformer. So it doesn't take any inputs. It just takes text and generates the next word by word. So you started with a prompt. So the thing in green is a prompt, like in the shocking finding, scientists discovered a herd of unicorns. And then it keeps generating content. The scientists named the population, and it's a very readable text. And it kind of makes sense as a story. So it can generate text to some extent. But if it goes longer and longer, you start noticing that it's losing track. And also, there is this n squared d factor in the attention mechanism. So if n, like if your number of words starts reaching 1,000, you'll still be okay with the transformer, but it gets slow, right? You get back to this thing that I was describing with RNNs, that you need to wait a month for your model to train. And this is really not fun, because Waiting a month for something that may not work is not nice. So could we make it better, right? Could we have the benefits of a transformer, but allow it to process very long sequences and run faster, not have this n-squared problem, and hopefully also, so the GPT-2 transformer was quite impressive, like could generate stories like that, but it had about a billion parameters. So that's a lot, right? There is a GPT-3 now that has 170 billions. So these are huge models, and it would be nice to be able to run them, like actually on your computer, right? But so 170 billion parameters, even if like 16-bit floats, that's like 300 gigabytes. You need to have that much RAM, which you can still buy and install in your machine, but there is no GPU that has that much memory, right? So you need either a cluster which like interconnects and share parallel model training and so on, or you need to think like, can I just do this with my RAM, and then can I find a better method? So we believe there is a better method, and we can go to the next slide with that. So that's what I was thinking about. How about efficiency, memory, and actually getting results? Let's go to the next slide. So the solution I want to tell you about is called Reformer. It's based on our paper from end of last year, which is an improvement to the transformer to make it handle long sequences and to not run out of memory when it's very big. So as you can see, like this is the table you've already seen, there is this n²d thing, and it's a problem when n gets larger. When n gets to be 10,000, the 10,000 squared is really inhibiting, but a book can have 100,000 words easily, right? It can even have 1,000,000 words. And maybe you need to look to the introduction before you write the end, right? So it would be nice to have long context. So how can we handle it? Let's go to the next slide. So what does attention do? You know, there is the softmax QK transpose. That's the core of it. So when it processes a single query, like a word, it will look at all the similar words. So the degree of similarity here is noted by the strength of the color. And similarity is between some linearly processed activation. So it's not looking for the most similar word, it's looking for the most similar activations in a processed sequence. So it may be looking for coreference resolution, for example, as on this slide. And it will pick a softmax of the things it's found. So a softmax basically means I want a small soft subset of the most probable answers. So a small soft subset is basically what people call the nearest neighbor problem. So I have a vector for it, vectors for all the other words, and now imagine this sequence is really, really long. So I would like to pick the nearest neighbors, the nearest vectors in this long sequence for the one I have. And the way we do it in the QK transposed and softmax thing is we just compute the distances between all pairs of words, right? So this is one way to compute the nearest neighbor, is to just go over all of them. But is there a better way? And if you go to the next slide, there is a better way, and it's been known in computer science for quite a while. It's an approximate way, and it's based on locality-sensitive hashing. So what is locality-sensitive hashing? It's an idea that you will assign a hash to every of these vectors and to your query, so that if you compare only with things that have the same hash, you're very likely to find your nearest neighbors there. So one of the easiest, but also the one we use in Reformer ways of doing locality-sensitive hashing is random planes. So if you have a number of points, right, like here, and you just cut them with the few random lines, and there is like log n of these random lines, so not very many, right? then points that lie on the same side of all of these lines are most likely to be nearest neighbors. So if you look at the picture, same side means in the same region of space delimited by these planes, right? So on the bottom, you have the green points, and they are nearest neighbors of each other, right? And so on the right. But if you look at the red points, right, especially the one that's marked here, it's some of its near neighbors are not on the same side, right? They're not red. They're not in this part of the plane, but they are in the upper part. And that's because it's a probabilistic method, right? It depends how you choose the lines, and maybe you've chosen them not well. So the thing you need to do here is to redo this a few times. And this is like the number of hashes, and then gather the nearest neighbors gather the regions from these few random choices. And that works really well. So on the next slide, we just use this random hashing idea for doing attention. So instead of the standard softmax QK transposed, we do locality sensitive hashing, meaning we slice Q and K with these hashes, only consider elements that land in the same hash and repeat this a few times. So that's easy to say. It's tougher to implement so that it works well on accelerators. So on the next slide, you'll see how we implemented this. And when doing this, we realized it's really best to assume queries are equal to keys. And it turns out in transformer models, this is not a problem. You just use the same linear matrix for Q and key, and that's all okay. So when you do that, then you get the hashes, and the hashes here are denoted by colors. So hashes, or in this case, buckets, because the same hash needs to fall into the same bucket. So you see, for example, you might want like the blue elements should attend to each other. So what's the, oh, there is a question. What's the intuition between considering the queries equal to keys? The intuition is as follows. You are the reason for the thing you're expecting from this attention layers in a language model is to look to words before you that carry some important information. So the linear matrix that you're using is selecting what part of information this specific head should be looking at. And for queries and keys, there is no fundamental reason for this to differ. Like when you have encoder-decoder attention, there is more of a reason to have a different query and key linear transformation. But in a language model where you have just the decoder block, you're looking into the past anyway. So you can just use the same matrix for constructing queries and keys, and it seems to work fine. I hope that that helps. So yes, so we use that, and it simplifies things because there is no two things, right? There's no query buckets and key buckets. It's just one set of buckets. So the operation we use, which is fairly reasonably implemented on GPUs and TPUs, is just sorting. We assign to every element the ID of its hash, and it's an integer from 1 to how many hashes we have, and sort by that. And actually, we sort like a secondary key to sort, which we just make by multiplying the integers and adding, is the time in the sequence. So the elements that were to the left remain to the left. The elements that were to the right remain to the right. So you see the sorted thing in the middle. So now we still have the problem that mathematically we should attend within the color, right? You should attend, all blue ones should attend to blue and nothing else, all yellow ones should attend to yellow and nothing else. But On accelerators like GPUs and TPUs, it's much better to not slice memory at random locations. It's much better if the accelerator can know that it will be attending in chunks of 4 or, well, actually 128 is usually a good number or something like that. So what we do is we chunk it, meaning we just brutally cut it at the boundary of 128, or well, on this picture it's 4. And then we will arbitrarily attend just for 2 chunks. So we will attend within the chunk and the chunk before that. So it may happen, like if you see the blue one is okay because the one from the chunk after attends to the chunk before and gets all the information. But if some bucket was overflowing that it would be more than 2 chunks, then we would not attend to some things that we mathematically should attend to. But, you know, it's locality sensitive hashing is a random thing anyway. So we take this as a hit, but get a performance improvement from, from doing these chunks. So that's how the LSH attention works. And now LSH attention, because it only attends within this constant chunk, we can go to the next slide. It decreases the complexity from n squared to actually n log n of this attention. So that's really nice. And if we go to the next slide, so we can build a transformer with this LSH attention, and that already decreases our computation time. That's very nice. But we still have the problem that if we build really big models, we'll be using a lot of memory, because now we've decreased the memory use and computation time for attention. But if we have the big N layers, then we still need big N times n times d memory, because, well, if you move a forward pass, you need to backpropagate, and every layer needs to store its activations. And to solve that, in Reformer, we use another trick, which is on the next slide. Namely, we use reversible layers. So a transformer is a residual architecture. And a reversible network is a tweak on the residual architecture that allows you to invert the layer. So let me take a moment. There was a question. So saying that chunking can hurt at the beginning of training, and it is true. So at the beginning of training, it takes a little bit longer for LSH to get up and train. But we've checked it on very long sequences, and it just takes a little bit more time. It's a probabilistic algorithm, right? So it will settle. You just need to give it a bit more steps at the beginning, but it's not that much, you know, compared especially to the fact that these models are usually trained for a while. Okay, so reversible networks. So in the standard ResNet, a residual layer is just x plus f of x, right? And if you have another residual layer, so f could be in the first step, it's an attention, and then you have a feed forward block. So the y is y plus g of y. This would be the standard residual architecture. Now, in a reversible network, you do these 2 steps at one on a vector that's chunked in half. So you come to the network with 2 vectors, x and y, x1 and y1. And you compute the first network on one half. Oh, sorry, you come to the network with x1 and x2. These are your vectors. And you compute the first half of your answer as x1 plus f of x2. So you keep one half and operate on the other. And then you compute the second half by keeping the second half of the input and operating on the first, on the thing you've just computed on the output. So, okay, that seems like, you know, okay, we've halved the vector, did some math. Why? Well, the answer is now from y1 and y2, you can recompute back the x1 and x2. And it's just by applying operations and going back. So x1 is just y1 minus, x2 is just y2 minus g of y1, and x1 is y1 minus f of x2. So this layer is reversible, meaning you can do a forward pass, and we can go to the next slide. You can do a forward pass without storing activations, and then do a backward pass and recompute it. And you're paying the price of recomputing, which is the price of almost like one forward pass, but the backwards pass is usually 3 times slower than forward. So instead of 1 plus 3, so about 4x, you have 1 plus 4, so 5, you lose about 25% of training time, but you gain as many as you had layers in memory use. So it's much more memory efficient, so you can now train a big model even on a single GPU. And so on the next slide, you'll see we made like a lot of tests for that. We checked whether this Q equals key influences anything, and actually it even makes things train a bit faster. We checked whether reversible layers, but just standard attention introduce things, and they seem to have very mild impact, at least up to like 12 layers. We haven't checked how it behaves when you go to like hundreds of layers. And it may be that reversibility, like that you need to forget if you have more layers. But at least until 12, this seems to not have an effect.
Oh, and sorry to interrupt, but just a warning, that is 3 minutes till noon.
Yeah, so we checked that, and the LSH attention, well, it's a probabilistic thing. So it depends on how many of these hashes you have. And if you have 2, then it's actually worse than the standard one. But as you go on, like with 8, it already seems to match the standard attentions on the problems we tested. So that was the next slide. And the slide after that, it's n log n versus m squared. So as your sequence grows, your speed ups become larger and larger. Okay, so that's the reformer, and yeah, I'm slowly coming to an end. So in addition to research, which is the main thing I wanted to tell you about, on the next slide, I also want to say, well, there is, I did a lot of coding and frameworks too, right? So I developed a framework called Tensor2Tensor, where the original transformer was written. And these days, I work on a framework called Trax, where we are working on this memory efficient training and on reformer. And we learned a lot of lessons in like how to do frameworks in the time. I will not tell you about all of them today, but you can go and check this out some other time. I do feel like we've learned a lot how to make the code cleaner and more usable, while also being more memory efficient. So if you could skip the whole section until the outlook. The outlook. So yeah, so with Reformer, what we've managed is to run on a single GPU a model with 1 million tokens. So that's like a long book, right? It runs on examples of this size. So this means it can generate like higher resolution images, music, maybe small videos. It can train on whole books. And where does that take us? Sorry, one slide up. Just one after Outlook. So one down. Yeah, here. Oh. So yeah, one before this one. So we did this work, and then there was this thing called GPT-3, which which is a very big transformer model, but just with a context of 1,000 words. And yeah, I'm very excited that, you know, combining these techniques, like training a really large model that can handle very long context, might give really amazing results. Like maybe you can just do some web search and provide the model. Maybe you can like just talk to it, give him all your previous emails, and it will write a new email for you. I think it's very exciting to push these models towards really long sequences and large models. And I do believe that we can make these large models, you know, train at home on a single GPU machine or on a few GPUs. And well, reformers we didn't make super large, but that's what I'm working on currently to hopefully we get to GPT-3 size, but we can all train this, not use just some API, but actually have access to the full model. So that's it. Yeah, and if you want code and more in-depth things, it's in Trax. So as you saw on the next slide, it's there. And yeah, I think my time's also up. So if there are questions, or should we, Keith, what's the next step?
So right now there's what's called an AID lunch, but well, first off, I do want to thank you again for coming, and the many people who are able to listen to your talk are surely thankful as well. Let's have time for one question, and sadly, because I'm sharing the screen, I cannot see Zoom. So if there are people who've raised their hands, or maybe even better if they could just put their questions on chat, maybe you could find one that seems most interesting and relevant, and then you could answer one.
So I've got a question, if I may. This is Ulf.
Sure.
Cześć Lukasz. So I have a high-level question. So your work has contributed tremendously to NLP. For the future, how do you see the relationship between your deep learning on the one hand side and traditional computational linguistics with linguistic knowledge on the other side?
Well, I believe it's quite important to actually think of linguistics and continue thinking deeply about it, because we should not forget, like, these models can generate amazing text, and that's great, right? We have powerful tools, but we need to be very careful about studying them rather than falling in a magical belief that they will solve all our problems. That's definitely not the case. Meaning they can generate very fluent language, but does this language make sense? How can we even measure whether something makes sense, right? And I feel like traditional linguistics has a lot of answers to the questions that we'll be facing, to the questions of how do we measure understanding, right? How do we go more into the semantics of things that can be generated? So I feel like deep learning provides amazing tools, but to know what to do with them, we need to look back into linguistics and language and semantics possibly, and start asking questions like, what are the right metrics? Like perplexity, BlueScores, they're all good metrics. And translation, when you have references, provides you a very easy answer to, is this a good translation or not? It's much harder to say, is it a good summary? And it's incredibly hard to say, is it a good book, right? But it's sometimes easy to know it's a bad book. And we'll need to, like, as we go forward, we have these amazing tools. We'll need to invest more and more into understanding how do we actually evaluate them, and you know, what they are useful for and where they are dangerous and actually not useful to the part of potentially being harmful. So that's yeah, I think that's where I think the more traditional methods have a huge way to contribute.
All right, thank you again. And again, because we're out of time, I'm afraid we're going to have to stop here. But I do want to talk to you just afterwards, Lukasz. And everyone here, feel free to reach out to him afterwards. You're again, you've done such great work. It's a pleasure to have you here. And
thank you very much for the invitation. It's great to be there, and I'm happy we managed to make it work.
Right, and I hope that after all this COVID stuff, we can actually meet in person.
That would be very nice.
Thank you.
Thank you.
With that, Peter, you can stop recording. And goodbye, everyone.